When we use a camera to ensure clarity of images, we adjust the focal length of its lens based on the distance of the object. How does your eye do that? What happens when you switch from reading a newspaper to looking at the television at the end of the room? Or look up to see a plane in the sky? As mentioned earlier, ciliary muscles help obtain the focus of objects located at different distances. Your eye can change the focal length of the lens in a fraction of a second when you look at another object. This ability of the eye to change focus for objects at different distances by altering the curvature of the lens is called accommodation. For an object to be seen clearly, the image must be formed on the retina. The distance between the lens and the retina is fixed. So, how do you think the eye is able to focus on objects at different distances? Remember the relation between the object distance u, image distance v, and focal length f of a lens? Let's refresh your memory. The relation between the object distance u, image distance v, and focal length f is represented by the expression 1 divided by f is equal to 1 divided by v minus 1 divided by u. In this relation, all distances are measured from the center of the lens. Applying this formula for the eye, image distance is the distance between the lens and the retina, which remains constant. The object distance is the distance of the object from the eye lens, which may vary. Therefore, to form a clear image of different objects at different distances from the eye, the focal length of the eye lens has to be changed. And how do we do that? By altering its thickness, of course. For example, to focus on a distant object, the eye needs to increase the focal length of the lens. To do this, the thickness of the lens should be decreased. Conversely, to decrease the focal length, the thickness of the eye lens should be increased. To accomplish this task, ciliary muscles are used. The contraction and relaxation of these muscles helps to alter the curvature of the lens. For instance, let's revisit the scenario when a person switches from reading the paper to looking at the television at the end of the room. As the television set is relatively far from the eye, the light rays from the television are almost parallel and do not require much convergence to be focused on the retina. Hence, the focal length of the crystalline lens needs to be increased to focus on the images on the television. In such situations, the ciliary muscles relax. This decreases the lens thickness, in turn increasing the focal length for clear vision. On the other hand, the light rays from an object located close to the eye, like the newspaper, are divergent and require relatively more convergence. Therefore, to focus on such objects, the focal length of the lens should be decreased. This happens when the lens is comparatively thicker. Therefore, to focus on objects closer to the eye, in this case the newspaper, the ciliary muscles contract. This increases the lens thickness, in turn decreasing the focal length. In this way, accommodation of lens helps us to focus on objects at different distances and see things clearly. So, think about what happens when Jerry switches from looking at the sunset to solving his physics problems. Do you think his ciliary muscles need to work in this scenario? Let's see. Looking at the sunset, Jerry is seeing a distant object. However, When he works on his physics questions, he is looking at his notebook closer to his eyes. The ciliary muscles in his eyes will need to accommodate this change.